Okay, good morning. Week 12 Friday. Before I start, I want to talk about review of term test 2. I will set a date that you can collect your term test 2, and you have to collect through your TA. Okay, so I'll put on Avenue to learn when are the TAs available, and you have to go and visit them. Okay, this cannot be done online, unfortunately. Okay, because they can't scan every term test answer and then mail it to you. Okay, you have to be at McMaster to collect them. Okay, now I will announce the date when to contact your TA. Okay, so you arrange a meeting, or I will ask the TA when they are available. Okay, I'll ask about their location, then you can go and see them on your own. Now, today we are going to look at ductile yield criteria. We're going to start with Tresca, and we're going to finish off with Bommesis. Okay, and I'm going to do an example that is very, what I call a complete design process in selecting materials. Okay, so on Wednesday we talked about the maximum shear stress criteria. Okay, so we have the general form of the criteria is the maximum shear stress equals shear yield divided by 2, right? And this yield over here, you have this, okay, is a material property. That you get from materials handbook. Okay? And if you look at equation 2, okay, so all this I did not elaborate on Wednesday. I do apologize. All these are in fact analyzed using 3D Mold circle. Okay, I realized I did not emphasize that. Okay, so the first condition is one of the principal stress. Okay, so stress A and stress B are the principal stress. Okay, I'll add on down here. Stress A and stress B are the principal stress. Okay, so one of the principal stress is equal to 0. Tau max is equal to half the absolute value of sigma max. Okay, so that's one condition. The second condition is where, again, this is 3D Mold circle, where stress A and stress B are not equal to 0, okay, when one is positive or one is negative. Then you have to check with this condition where tau max is equal to half absolute value of maximum stress minus by minimum stress, okay? So whether you are going to use equation number 2 or equation number 3, you have to construct what? 3D Mold circle. Okay? You cannot just use 2D. Okay, right. Sometimes you can, as I say, I mean, I usually check with 3D and it's good practice. Okay, but my conclusion is 90% of the cases 2D Mold circle is sufficient. Okay, that's what I have to say. Okay, so the next thing I'm going to construct now. Any questions so far? Anyone? Don't see anything. Anyone face to face? You have questions? Nothing. Okay. So now we are going to. I'm going to draw another graph. Okay, another graph. So this is still on Tresca criteria. Okay, this is still on Tresca. Okay, this is still on Tresca criteria. So I'm going to construct the graph. Now this is not Mold circle. Okay. So on the x-axis is my stress A, and on my y-axis is our stress B. Okay. So we know that stress A and stress B are the principal stresses. Okay. And then we are based on Tresca, all these are your U point. Okay. So the U point, wait, I will say why I say based on Tresca. Okay. So this is our U point. This is our minus U. Minus U. Okay. So Tresca criteria assume that the U strength in tension is equal to the U strength of compression. Minus is compression, right? So i.e. U strength in tension on tensile and compression have the same magnitude. Hey, come on, UT. Okay, so by looking at the condition that they have, they constructed a map. Okay, when I say a map where the operating to identify where the operating region are. Okay, and it looks like this. Okay, I'll draw up to you for you. It looks like this. Now, stress A and stress B are your principal stress. And I'll elaborate again, this is not most circle. Because when you look at this, you thought, oh, this is most square now. Again, it's not. Okay. Okay. So this is the operating bracket of Tresca criteria. And stress A and stress B combination must be in the shaded region. Okay? They must be in the shaded region. Right? So stress A and stress B. Okay. Now stress A and stress B, they are linked to one another. I'll call that they are coupled. Okay. They are linked to one another. Okay. Must be within the shaded region. Okay, must be within the shaded region. If not, the material, okay, the material will yield outside the shaded region. Yield means what? When we say yield, it means elastic to plastic behavior. Okay, so the deformation will be what? Permanent. Okay, you don't want to do that. Okay, you don't want to design something and then when there's a load, the deformation is permanent, and when the load is released, the structure is tilted. Okay, you don't want to do that. Okay, so now we will pick 5 points. Okay, we'll pick 5 points. Okay, so the 5 points that we are going to pick. This is our point 1. Okay, this is our point 2. Somewhere in here. Okay, this is our point 3. Over here will be our point 4. And I'm going to pick somewhere outside This will be our 0.5. Okay. So if we look at 0.1, when we look at 0.1, 0.1, we have stress A is equal to stress U, and then we have stress B is equal to 0. Okay. So we are going to construct the mole circle now. Okay. And I'm going to draw a box. And you have seen this before. When I say you have seen this before, what do I mean by that? Okay, it means that we have done one example where we also construct the box. Okay, so this is not a surprise for you. So this is our normal stress, right? This is our normal stress. This is our shearing stress. Element rotate clockwise, element rotate anti-clockwise. Okay. And over here, this is our stress U. This point over here is our minus stress U. Okay. This point over here is our stress U divided by 2. Over here is minus stress U divided by 2. Okay. Oh, you can see the lines good. Okay. And I'm going to copy this graph because I need to use it quite a lot later on. Okay. Okay. So if you look at point number 1, okay, P1 over here, where stress A is equal to stress U. So this is your stress A, right? And stress B is equal to 0. That's point A, point B is over there. Now we can construct a circle. And you will realize that the circle is within the box. Yes or no? Right? Within the blue box. Okay. So this is okay. It will not yield. Right? Like what it say down here. Okay. P1 will not yield. It's at the boundary. You go a bit bigger, you are done. Okay. So now if we were construct point 2, okay, so point 2 is where you have stress A is equal to stress U, stress B is equal to stress U, right? So when we construct that now, okay, I want you to come on, move, and then when we case. For this case, is very interesting, right? Right. I'll tell you what interesting. Point A is here. Point B is also at the same point. So there is a possibility that you don't get a circle. Okay, right? That's a possibility. You get both stress A and stress B at the same point. So now, can you draw a circle? It will be a very good question for your final exam, isn't it? Draw a stress state where you cannot construct a mole circle, or mole circle is a dot. Yes or no? Okay. So here you go. So this is just a dot. Now, when we go into P3, okay, point number 3, where you have stress A and stress B, okay. So point number 3, again, very same situation where stress A is equal to stress U divided by 2, and stress B is also equal to stress U divided by 2. we end up in the same situation. If we do 2D mole circle, yeah, 2D, not 3D. Okay, if we do 2D mole circle analysis. So now over here, right? We have a situation now where our stress A is good to so this is at this point is both your stress A and stress B, right? So it's again at a single point. Okay. Now I'm just going to focus on stress A and stress B for now. Okay. I'm not going to include the third stress Z. Okay. I want you all to learn the principle of the fracture. I mean of the yield first, and later when we do a example, it'll be 3D. Then we focus on 3D. Okay.